Previously, we did an example to check the slenderness of a column, which is the ground floor column B3, assuming that the structure is braced. The column was found to be a short column. In these videos, we're going to deal with the same column, only that we assume that the structure is unbraced. The purpose is to demonstrate the differences in terms of the calculation steps, as well as the classifications of the column when the structures changes from braced to unbraced. Refers to the structural key plane, the elevations of the structure, the dimensions and the specifications given. This is the setup of the column. At the upper end, you have 3 beams connecting to the column, whereas at the lower end, you have 4 beams connecting to the column. The process to determine the slenderness of the column comprises 2 main parts. First is to determine the slenderness ratio. Second is to determine the slenderness limit. You will compare the slenderness ratio of the column against the slenderness limit. When the slenderness ratio is less than the slenderness limit, we can say that the column is a short column. Otherwise, the column is considered as a slender column. The calculation steps to determine the slenderness ratio as well as the slenderness limit vary slightly depending on the structures, whether it is braced or unbraced. In the previous example, we assume the structure is braced. That means in the process of calculating the effective length, this equation shall be used. Now, the structure is considered unbraced. Instead of using these equations, this equation shall be used. This will give you another effective length, which ultimately will change the slenderness ratio. Another major difference between the braced and unbraced structure lies with the slenderness limit. For a typical braced structures, you may use either of these 3 equations, subjected to the load arrangement. We have discussed about the concept where different load arrangement will give you different response of the column. As a result, the slenderness limit that you use differs. It depends on your design assumptions in terms of the load arrangement, as well as the conservativeness that you intend to have. However, dealing with the unbraced member, you will have to use this equation. These 2 equations are not applicable. Now, if you have difficulty understanding why this equation is applicable to the unbraced member, you may adopt the principles that we have discussed previously regarding the response of the column due to the deformations of the structures subjected to external load. For better understanding, you may refer to this diagram. First, you need to understand the principle of braced and unbraced structure. The meaning of the braced structure is you have a proper mechanism to resist the horizontal load. This can be due to the bracing or the shear walls. These members may be used to withstand the horizontal load, leading the structures, particularly column, only need to resist the axial loads without any horizontal deformations. As a result, both ends of the column will be in the same axis. There won't be any second order moment due to the P delta effects. However, when it comes to the unbraced structure, the entire frame behave as a cantilever members. Since you do not have any mechanism to withstand the horizontal load, the resistance to the horizontal load, it will be due to the cantilever actions of the column. The structures is likely to sway due to the horizontal load. As a result, the column will be subjected to axial load plus the second order moment due to the P delta effects. Having this understood, let us come back to the response of the column here. When the structure is unbraced, that means the entire frame is subjected to the horizontal deformations. Due to these horizontal deformations, you will expect the joint to move horizontally. Taking this joint as an example, since we want to calculate this column, when the structure is subjected to the horizontal force, the joint move. Assuming the joints of the members are monolithic, that means the column will be 90 degrees to the axis of the joint. At the same time, the lower end here, you assume without any movement. Or you may assume that the horizontal movement of the lower end of the column is not as significant as the upper end. When the joint here remain in the same positions, 90 degrees to the axis of the joint, you will expect the column to behave something like this, as indicated by the red line here. You can draw an imaginary line connecting both ends of the column. Draw a line here. You will see the response of the column something like this. Now this response, it will be identical to this. Because of this response, that means the slenderness limit, you will be using this equation. Theoretically, this and this will not happen in the unbraced structure, and therefore these two equations are not applicable to the unbraced structure. Having this understood, let us come back to this question. We will start with determining the slenderness ratio of the column. First, we need to determine the effective length and then the radius of gyrations. The effective length will be using these equations since it is an unbraced structure. You will need the case. K1 refers to the stiffness at N1, the upper end, and K2 refers to the stiffness at the lower end, N2. To calculate this K here, you need to get the stiffness of the column as well as the stiffness of the beams. This K represents the relative stiffness of the column as compared to the beams. That means you need to get the I and L first in order to get the K, so that you get your L naught, and then to get the slenderness ratio. We're going to go step by step. First, get the moment of inertia. The moment of inertia is taken as BH power 3 per 12. The beam size 150 times 450. B times H power of 3 divided by 12. You get the I, which is the moment of inertia. In the major axis, you have only one beam from one side without any beam from the other side. That means for the top end of the column, there is no K here. In the secondary directions, you will have beams from both ends. Get the effective length also. This member is 6 meters and this members is 2 meters, 2 meters. That gives you 6 meters, 2 meters, and 2 meters. Find the stiffness of each member. Getting the I divided by L, you get the K of the beam. You will do the same for the other members. And then repeat the same process for the joint at the lower end of the column. Up to here, the calculation steps shall be the same as the previous example, since the setup of the members are the same. Next, you will need to determine the properties of the column, the dimensions of the column. The cross-sectional area, it will be the 300 times 150, which is the size of the column, and then you get the sectional areas. The story height 4 meters. Same set of loading, axial load 49.12 kN. Now you assume that the structure is unbraced. Get the clear height of the column, which you may refer to the elevations of the structure. 4 meter story height minus the height of the beam, you get the clear height 3.55. And then get the moment of inertia. The equations, it will be the BH power 3 per 12. Since now the column sections is a rectangular shape, that means the BH swap depending on the axis that you are calculating. Dealing with the major axis, that means the B, it will be the shorter one, and the H, it will be 300. To get the moment of inertia for the major axis, you will have BH power of 3 divided by 12. If you are calculating the moment of inertia for the minor axis, now it will be BH power of 3 divided by 12. This gives you different moment of inertia. And then calculate the stiffness. The moment of inertia divided by the clear height. Again, up to here, the properties of the column as well as the property of the beam, there is no difference between the braced and the unbraced structure. Due to the same set of stiffness for the column and the beam, your K1 and K2 for the major axis, as well as the K1 and K2 for the minor axis, it will be the same. Substitute the K from the beams and the K for the column into the equation. You get the K1 and K2 for the columns in the major and the minor axis. The K should be at least 0.1. When the calculated K1 and K2 is less than 0.1, you will use 0.1. This concludes the K1 and K2 for the major and the minor axis as indicated here. Starting from here onward, the calculations differ between the braced and unbraced structure. Using the same set of K1 and K2 as per the braced structure, but now the equations used to determine the effective length differs. It is determined by either this or this, whichever give a greater value. The L here represent the clear height, and the K1 and K2s are the one that calculated previously. Substitute the K1 and K2 as well as the L into the equations. You get your effective length higher than the story height. The story height is 4 meters, but the calculated value for your effective length are more than 4 meters. Next, you calculate the radius of gyrations. No differences observed, since this is purely geometrical property of the column. Because of the L0 here change, your slenderness ratio changes. The slenderness ratio is calculated by dividing the effective length with the radius of gyrations. And then you're going to compare with the slenderness limit. For an unbraced structure, this equation is used. You have the NED, which is 49.12 kilonewton. You have the areas of the column, which is calculated by multiplying the B and H of the column. Next, you need to calculate the FCD. FCD is calculated by using this formula: 0.85 times FCK divided by partial factor of safety of concrete. FCK is 25. The partial factor of safety is equals to 1.5. You will have your FCD equals to 14.17. Substitute into the equation. You get your slenderness limit 38.9. You see now the slenderness ratio is greater than the slenderness limit. That means this column is no longer a short column. It is in fact a slender column.